Okay, so what we're going to do here is we're going to do a design problem. As I mentioned, this is going to be a design. We're going to walk through some of it. This is going to be the project that we're going to be installing the end of May. So it'll give you a little bit of orientation as to what we're going to be dealing with. I'm going to jump into the screen share. The first thing that we're going to want to do is, well, let me share the one-line drawing. Okay, so this is the one-line drawing of the project. And this is, it's not 100% accurate because we changed some of the information. I changed the solar panels. Instead of Canadian Solar 355s, we're going with Jinko 400 watt panels. The only reason for that is because that's what the distributor had. Either panel would service our needs, but that's what we're going to go with, 400 watt panels. Notice the inverters, the microinverters are the 295 watt. So we're going to be dealing with the clipping issue with the 295 or 400. And the advantage there, let me do a quick drawing there, just to reiterate what clipping is with clipping, in this situation, if we talk about, here's your curve, and the microinverters will generate a maximum of 295 watts. So let's say this is the day that we hit solar noon, and then we find that it tails off at dusk. Okay, so if this is 295 watts, this is what a 295 watt panel and a 295 watt inverter would look like. So it would capture 100% of everything that's being generated under standard test conditions. If we go with a 400 watt panel, now that curve's going to look something more like this. And what's going to happen is this portion of it is going to be clipped off. So if this were 400 watts up here, this amount of power in here is not going to be captured. That's going to be lost. Even though the panel's generating it on a standard test condition day, that's not going to be captured. But this power here will be captured with the bigger panel. And typically the two shoulders are more than what's lost by clipping. So even on a standard test condition day, we're generating more power with the bigger panel than we would, even though we clip it. But the reality is most days, we would never hit 400 watts because there's a certain amount of cloud, temperature's too high, whatever. So I would say 95% or better of all days, the curve is still going to be under that 295 clip point. So what we usually find is we try to go with a 1.2 or a 1.3 clip or load to inverter ratio. So in this case, we would find 400 watt panel, that's DC, 295 AC, and that's going to give our ratio. And in that case, it's going to be 400 divided by 295 is a 1.35. So it's a little bit high, but not terrible. So we've got a 1.35 load to inverter ratio there. So that's just what's known as clipping. Okay, so we've got our design. So the first thing we're going to do is jump in and we want to look at PV watts. So in this instance, the address is here in Columbus, 3107 Wareham Road. That's in Upper Arlington, if you're familiar with Columbus. And we're going to look at PV watts. Now, for this example, we're not going to size it to meet all of the load because Tim already decided that the size that he has, the area that we're going to mount is limited. So we've already determined we can only fit 10 panels in there. So it's going to be a 4 kW system. And we're going to go with about a 6% system loss. How did I come up with 6%? I've been allocating 3% for the inverters. If you look at the microinverter spec, you'll find that those microinverters are about 97% efficient. I'm going to go with a 2% voltage drop because we're going to size our wire so that we don't exceed that. And about a 1% for miscellaneous connectors, things of that nature. So I'm going to go with a 60. We're orienting it true south, so that's going to be 180, tilt of 20 degrees. So now that's going to tell me that this particular system is going to generate 5,729 kilowatt hours per year. It's going to have about 4.62 hours of insolation on average each day. Notice, of course, in the summer, we're getting a lot more insolation than we're getting in the winter months with this orientation. That's pretty standard with North America, with this part of the country, with this part of the world. We just have longer days, more sunlight in the summertime. So I know I calculated before that if he was a standard home with 900 kilowatt hours per month load demand, this would service only about 50 to 60% of his load. So this array is not going to do 100% of the load demand. It's only going to do 50 to 60. We're going to size it in a way that we could add later. But for right now, it's only going to do that. Somebody have a question? Nope. Okay. All right. So that's what we're doing. And in fact, let me stop the share on this, and I'll jump in and show you why we're limited. I got to find my. There we are. He's putting it on a pavilion. So this is the pavilion that's being built. I think it's pretty much built at this point. So here's the rafter structure, and here would be the deck, the top where we're going to be mounting it. They'll put a metal roof on. And when we added up all the space that's available, it turned out we only can do 10 panels based on the size of the panels we have. And notice how the rafters go north and south here. Well, that means our rails have to go east and west to be supported by multiple rafters. So the footers are going to be put into multiple rafters. If we tried to do a north-south railing system, that would mean each rail would just be mounted to one rafter, and that's not good load distribution. So we've got to go with an east-west rafter orientation, or rail orientation. And since we've got the rails going east and west, that means our panels are going to be portrait because they're going to go up and down. They always get bisected across the long side of the panel. So we're going to end up with 2 rows, 5 panels wide, or 5 columns, 2 rows. And that's just the maximum that'll fit on there on that roof. So 10 panels, that's our max. That's how we came up with that. Everybody clear on that? It was just simply a spacing issue. All right, so let's see. Oh, yeah. Let's go into the, going to jump into the online railing system. So Iron Ridge has this nifty design tool. And what it does is you simply plug in the address here, and it will then, first thing it does is it finds the location just to verify with you that this is the house you're talking about. So this is Tim's house, where the pavilion has been built right back in here. So the array is going to be there. Now, bear in mind, Tim and I have talked about this. He's decided that in the future, he might add some panels on this section of the roof. It's not ideal. It's facing west. And this section of the roof, which is pretty good, it's facing, or this one over here, facing south. So again, this was my first choice to put it here, but he wanted to put it on a pavilion in the backyard, which is fine. So if he does decide to double the system, he'll probably put some here. And then the meter rests right in this section here. So we'll have to trench from there to here to run the wire from this array. But then if we add this array, we'll just go down the side of the building and over and connect in. And that's where the second branch circuit would hook into the end phase combiner box. And if we decide to add a third, then we would take this array and come in and connect in there as well. So this is how that works. Now, one of the nice things that this system does is as soon as you put in the address, it already calculates the snow loading, it calculates the wind speed, it does a lot of engineering calculations. It even does some seismic load calculations. It asks you to put in the panel. So there's a lot of different panels. You can select which ones you want. You can go down through. There are literally thousands of different panels that you can select. I selected the one that he's buying. So that's in there. Now it knows the thickness of the panel and it knows the dimensions of the panel because that's part of its database. That's going to be important. Now it asks you what kind of roof you have. We're going to be dealing with a metal roof. If it were composite shingle, we'd be putting that in there. So I'll select that. Then it'll ask us for the type of attachments. If I had selected shingle, it's going to give me different options. You know, what kind of, do I want the flash foot, whatever. But with the metal, it only gives me the one option, which is the L foot. It asks me what height. This is a single story, so up to 15 feet. That's going to adjust the wind loading. If I go up higher, it's going to have more wind. What is the slope? Well, I'm going to say that it's 18 degrees. What's the rafter spacing? I know these are 16-inch on center. And this is your seismic. It already did that. I'm going to save the roof information. Now, this has already been done, but you can do it if you want to. You would just pick, you'd click here to add. You can do it graphically or textually. But what we're doing is 2 rows of 5. So here's our graphic orientation of our array. And then it asks you to pick which of the railing systems. We're going to use the XR1000. This is the least expensive of the units. And we're going to use 14-foot lengths. We'll cut them on site. And here it's giving you just some information about that. It's already pre-populated. There's some interesting information like 10 modules, portrait orientation. The whole unit, the roof, is going to weigh 580 pounds. That's going to give you some shipping information there. It's telling us that it's 2.6 pounds per square foot, dead weight, dead load there. And now it's going to start telling us how many bits of things we need. So if I click on the bill of materials, it will now calculate how many rails do we need, how many clamps are we going to need for this unit, how many end sleeves, stopper sleeves, grounding lugs, and it's giving us a retail price on all this stuff. So it's telling me retail wise, my racking system is going to cost about 690 bucks for this particular system. Now it turns out I can get it cheaper than that from distributors, but this is kind of a worst case scenario. So that's kind of a handy little thing to tell you. It's price per watt, 17 cents per watt for our system, for the racking, only for the racking. Okay, so once I have that information, I use that when I went to put together a bill of materials. So the bill of materials, this was our first run through on the bill of materials. And the first thing I did is put in all the numbers of the stuff that I know we're going to need. And I looked up on Alt-E because I like their website just to get a price from them. He then took this list and went to McNaught McKay in Columbus to get a bid price from them. And I plugged that in to this same spreadsheet. So we've got the panels, we've got the inverters, We've got the bonding hardware. We've got the cabling. We've got the Envoy. This is the combiner box. And then some caps, things of that nature. We've got disconnects, lugs, double pole breakers, junction box, bus bars, a ground rod that we're going to need, conduits and fittings. I just said we'll get those at Home Depot. I don't know what they'll cost. I estimated 200 bucks. Some wire, the Iron Ridge stuff, I got that straight from the listing and then some labels. So when I plugged all these numbers in, we end up at about $5,000 or about $1.27 per watt for all of our materials. So you remember when I was telling you before that systems today end up costing in the neighborhood of $2.50 to $3 a watt installed. That's kind of a rough rule of thumb in the US. What we're finding here is that we can get the materials, even paying full retail for a small system, at less than $1.50 a watt, $1.27, $1.30. So that means the other half of it is going to be installation, profit, things of that nature. So by doing it yourself, you'll save about half the cost. That's just a pretty standard rule of thumb. The materials are only going to be about half the cost. Okay. Any questions so far on these items? Okay, then I'll keep moving on. I wanted to show you two here. Notice we said the end phase. Well, how do you do a wire size string calculations for microinverters? And it's fairly straightforward. I mean, I could just simply go into the installation specs and it says your branch circuit capacity for the IQ7 Plus, if we're going to be dealing at 240 AC, which is single phase, maximum number in a branch circuit is 13. That means I can't hook up more than 13 of these microinverters in one branch circuit. And the reason for that is the proprietary cable is 12 gauge. And if we look at 12 gauge wire, we're going to find that I've got the table here. I need my tab to move down. Hides it there. All right, yeah. The ampacity table here from the NEC. This is table 310.15B16, an easy number to remember, right? So these are the ampacities for your wire. Well, look at 12 gauge. If you're dealing with TWUF wire, it's 20 amps. If you're dealing with some of these type wires, a mid-range temperature wire, it's 25 amps. And for the high temperature wire, it's 30 amps. Now, PV wire is considered high temperature. So you might think that you want to just go with 30 amps. That'll handle up to 30 amps. But the assumption is, because we don't know the rating of the terminating points, we're always going to read our ampacity rating from the lowest temperature column. So let's just assume 12 gauge cable only has an ampacity rating of 20 amps, regardless of the type of wire we're using. So in this case, 20 amps, well, if we saw before that, that the ampacity rating, the output from this microinverter, it'll operate at 295 volts, or sorry, volt amps, or basically watts, and 240 volts. So we end up generating 1.21 amps per inverter. And when we hook it into this parallel, we're hooking it into the proprietary cable, we're making a parallel connection. So every time we add a microinverter to this cable, we're making a parallel connection. So what happens? Voltage remains the same, amps increase. So if I have one microinverter, I'm generating 1.21 amps. 2, I'm going to be generating 2.42 amps. 3, 3.63, and so on and so forth. By the time I get up to 13, I'm at 13 times 1.21. I'm generating 15.73 amps. Okay, but the NEC says I need to multiply that times 1.25 for a safety margin. And now I'm up to 19.66 amps. And we said the maximum capacity for 12 gauge cable is 20 amps. That's why they've limited it to 13. That's the most you can do with the safety margin and still be under the rating of 12 gauge cable. Now, from the combiner or from the junction box at the array, I'm going to recommend that you don't use 12 gauge cable, that we use 10 gauge cable. We could get by with 12 gauge cable, but my recommendation with these systems is never put in anything smaller than 10 gauge. That will help you with a lot of mistakes. It'll also help address voltage drop, because you may be going a significant distance from the array to the connection point, and that voltage drop, if the cable is small, you're going to get excessive voltage drop. So let's go with 10 gauge cable, even though it has a 30 amp rating and all we need is 20 amps. The difference in cost between 10 gauge and 12 gauge is minuscule compared to the overall cost of your system. I don't understand why they don't put 10 gauge cable in every house and every circuit, but I guess builders are cheap and $10 here or there is a big deal to them. But for us, we're independently wealthy. We're going to be doing this thing right? So besides, it's not your money. You're spending the customer's money. So who cares, right? Okay, so everybody clear on that? Now notice these systems are 240 or 208. These microinverters will deal with either one. With 208 volts, because the voltage is lower, the amps will be higher because the watts are the same. And notice they refer to the watts here as volt amps. That's because it's basically a generator. So watts is a measurement when you're consuming energy. Volt amps is a measurement when you're producing energy, and they're not necessarily the same thing. In a purely reactive load, they are exactly the same thing. In a purely resistive load, they're exactly the same thing. But if you've got a motor, they're going to be slightly different. There's going to be some issues there. All right. Anything I should, and notice the efficiency. Remember, I told you it's about 97% efficient. In this case, it's telling us that its weighted efficiency is 90%, 97. Its peak efficiency is 97.5. So we're just going to assume 97. So that's where I got my 3% inefficiency for the inverters. Now we're going to take these things from the junction box, and the junction box in this case is simply a transition point from the proprietary cable to the cable that we're going to be running in our conduit. And it's usually a different kind of cable. I think we're going to be using UF wire in this case, underground feeder wire. We could use PV wire. It's a little more expensive, but we'll figure that one out as we go to buy the wire. Doesn't really matter. It's just that because it's going to be underground and conduit, we want something that's highly resistant to moisture. That's the big issue for us, because in case that conduit leaks at some point, we want the wire to be resistant. We'll go into the combiner box. In this case, this combiner box is a proprietary thing from Enphase. It has the communication software built in. So that's a nice thing. We don't have to worry about the communication. It will accept up to 4 240 volt circuits. So we're only bringing in 1 branch circuit from this array, but we could bring in up to 4. Or we could bring in up to 3 with a battery backup. So that's good. So a total of 80 amps. That's what this unit is rated for. And as we discussed, in our last call just an hour ago or so, it has a 120 volt service plug here, accessory receptacle. So you can utilize power from that port as well. And in this case, I'm hoping we'll be able to run power from that directly out to the pavilion. So once we open up that trench, in this case, we're going to have one conduit going from the array to the combiner box. And then we're also going to have a second conduit with power going from there back to the pavilion so that the homeowner can use lights, maybe a ceiling fan at some future point, whatever. So he's got power out there in the pavilion. And we may as well put those both in when we've got the trench open. You know, it's a lot easier. And bear in mind, because these are two different circuits, we can't put them in the same conduit. We've got to have two different conduits there. So, and it's just good cable management anyway. So we'll see how that all works when we're out there. Okay, so any questions on the combiner box at all? Okie dokie. So that's how you do wire sizing with your N-phase microinverters. It's kind of the same way with power optimizers. If we're going to do wire sizing with power optimizers, we're going to simply look at the specs, and it will tell us based on the unit we're using how many we can hook up in a string in order to stay within their guidelines. So remember when we're doing sizing in a standard string, when we have to get what is the temperature differential between on the coldest day ever and standard test conditions, and then we find the VOC and we find the temperature coefficient for VOC, and we do all of those calculations. None of those are required for microinverters or power optimizers. It's just simply a specification in the system. Let me just share real quickly. I think I had the one line drawing up there, but in case I didn't, I want to make sure I talk about that real quick. Waiting for that to go, yeah. So this is the one line drawing of what we're going to be doing. And the issues, notice down here at the array, we will be putting in a separate ground rod down here, or grounding electrode. From our junction box, we'll be bonding all of these panels together through the railing system. Then there'll be a grounding lug on the rail. We'll hook it into a grounding bus bar in this junction box. And then we'll run a 6-gauge bare copper wire down to the ground and connect it to a ground rod. There is an existing ground rod over here already, which the rest of the system will be connected to at the service panel. By grounding our system to the ground in the existing service panel, we connect into here. There is some discussion if these two were right next to each other or within a certain distance of each other, we would then have to look at bonding these two ground rods together. Otherwise, you're going to get a difference in potential on two separate grounds, and you may get a ground loop going on within your system. I've asked a lot of inspectors, I've asked different people, when do we have to connect those together? And the response is always like, you know, like that old definition of pornography. I don't know what it is, but I know it when I see it. You know, there is no number. It's not like if they're within 10 feet, within 20 feet, within 15 feet. It's like those two things seem too close together, bond them together. And so it's really going to be up to the inspector. Unless I know, John, you're an electrician. You got an answer for that at all?
Well, they got to be at least 6 feet apart. I know that.
Yeah.
So they got to be 6 feet apart. That being said, you know, a ground rod has a singular purpose. The only purpose of a ground rod is lightning protection. It doesn't do anything else. It's just to protect against lightning. So, I mean, it's kind of being bonded together would never hurt anything. but having them not bonded together just means well, it depends on where the lightning strike's going. You know, it's like if you have one ground rod not bonded to another one, you have more resistance to earth. If you bond them both together, you got half the resistance because you got two ground rods. So it's a good idea, but they have to be 6 feet apart. And you know, I will look through the code and see if I have a better answer for that.
Yeah, I
But
would
they're
agree
only
with
lighting
you.
protection. They have nothing to do with the function of the electrical system.
Well, I'll agree with you to a point on that. For the array out there, that's the primary issue. But my understanding also is if there is a short circuit of some sort, or, you know, it provides a clean pathway of any stray electricity, whether it's lightning or a fallen wire or a short, it gives it a clean pathway to ground. Rather than allowing the individual, when he touches that metal piece, to become the pathway to ground. So it isn't for the functionality of your system, but it is to take stray electricity and give it a path of least resistance to ground. So it's a safety thing. Lightning is one of those. But for instance, if a power line fell on your system, you know, and is discharging electricity, you want to give it a pathway to ground. If a wire is pinched and maybe that power is now those electrical or those metal components are energized, you want to have that have a pathway to ground. And within our system, there is a ground fault detection device in the inverters. And if they sense any electricity in the grounding system, they will shut off. So the whole system will shut down because there never should be electricity in your ground system, in your you know, equipment grounding system. So that's so I'd say that it serves that purpose for lightning, but it serves other purposes as well.
Well, you know, we have talked about this because, you know, electricity is a loop, right?
Yeah.
And there's no reason for electricity going to Earth unless one part of that circuit is already at Earth, right?
Right.
And a electrical system, you know, you bond the neutral and the equipment grounding conductor. The equipment grounding conductor and the grounded conductor are bonded together at the main service panel. And that is to cause a short circuit in anything that is going somewhere where it doesn't need to be. It has no need for a ground wire or rod to function, right? The only reason you have a grounded electroconductor and a grounded electrode is to shunt lightning to Earth, because lightning circuit is from the clouds to the planet, right? And that's what the equipment grounding conductor and the grounding electrode do. So I have to figure out where in the solar circuit is any of that intentionally connected to Earth. I don't know where it is. Maybe it's not connected to Earth anywhere.
It will be. It will be through your neutral regardless. The wiring system, you know, will be connected into the ground that exists.
But once again, that's a reference point only to the greater. Well, we'll have to talk about it. It's not time place.
Okay.
And I will pursue this to figure
Yeah,
this
let me
out.
give you an example of a situation that occurred in our house. We have metal kitchen cabinets, and you know, it's the stainless steel kitchen cabinets. And my wife came to me one day and said, there's something wrong with the microwave because when I touch it, it gives me a shock. Well, my first reaction was it's a static electricity thing, and she's getting a little bit of a discharge. And I said, is that what it is? And he goes, no, it hurts. So I went over and started touching things, and I didn't get any shock. But then later I did. It felt like like touching a live wire. Well, what was happening is we had an electric tea kettle, and the base of it over time, the wires had rubbed, and the hot wire was energizing the metal countertop. So the metal countertop was live. It was basically like an exposed live wire. it did nothing. It just sat there, except when a human being would touch that metal countertop, it then created a pathway to ground, and electricity will flow through that individual. That created the shock. I wasn't getting shocked because I was wearing tennis shoes, so I was insulated, but she wasn't. So this is kind of, because if anything's connected in with the wire, yeah, the neutral is going to give you a path to ground, but the rails, the boxes, the framing of the panels, any of those could be hot through a short circuit of some sort. And the grounding system is designed to give a pathway of continuity to ground, so that that is the least path of resistance to ground rather than a human being touching, which then would create a pathway to ground and could be a fatal situation. So now the system is designed to recognize that there is now energy flowing through that ground and shut off. And then it gives you an indication that there is a fault and you need to go fix it. So those are some of the dual purposes of that grounding system. So it is a life safety thing. In addition to the lightning, lightning's probably the most common, but a squirrel chewing on things could be a ground fault as well. So it really is just to take a pathway of least resistance to ground for all metallic materials that are not intended to carry current but could, because they come in contact with current. Okay.
Well,
any other?
I know exactly what you're saying. I see
Yep.
the circuit in my head. We'll talk about this at a later date.
Okay, doke. Okay, so this is kind of what I wanted to go over on this particular one, give you an orientation of what we're going to be dealing with. I sent out an email to everybody talking about some of the dates. We will be meeting on the Friday. I forget the date. Is it the 21st, May 21st, to do some of the hands-on labs and do a review and take the certification exam. Then on Saturday, which I believe is the 22nd, we'll go ahead and do the installation. I don't think it's going to take more than a day. I just can't foresee that unless we have an unusual weather event. The amount of stuff we need to do with the people we have to do it with. So we should be all done. So you will have met the 3 issues for the certification. You'll have taken the course, which everybody will need to have completed all of the sections by then. We'll have done the hands-on material, and we'll have done the certification exam. Then your certification will be valid for 4 years, and it requires 6 hours per year. It doesn't have to be all in 1 year. So basically 24 hours over the course of 4 years of continuing education to renew that certification. And the education can be in anything that's, solar or electrical related. So in the case of you, John, your electrician's ongoing training you can get a twofer. You can get that as part of the thing there. I've also applied to the state of Ohio to try and get the 10 hours for this course. I submitted that at the beginning of the course. I haven't heard anything back from them. That's the electrical license, continuing education. So hopefully we'll get that from them, and this course will count for that for you this time around. Okay. Unless somebody has any questions, I'll call it a session here, and then we'll meet on Friday. If anybody's got an electric bill that you want to email to me, on Friday, we'll go ahead and design a system from start to finish. I would like to do one for a real house. If not, I'll just make up some numbers, but we may as well design somebody's house. You can take advantage of that. All right, so somebody email me your electric bill, and we'll get you a $5,000 solar design for free, right? All right.
Jay, I have.
Yeah.
I'm primarily taking this for CEUs.
Uh-huh.
And out of interest, my wife is all hot to put solar up here. So do I need to take the exam to get the CEUs for the class, a certificate of completion?
No. No, you'll get a certificate of completion. Yeah, no problem. I mean, I'd encourage you to take the exam because you can get the certification, but the CEUs would be a separate issue. Is this for your school, your ongoing school thing?
Yes.
Okay. Yeah, and as long as they'll accept your certificate, it'll have all the information you need.
I ran it through our committee before I agreed for the class, and they said they would accept it. So
Okay. So really,
So
then
I'm good
that's your
there.
choice.
So
That's
I
your
won't worry
choice.
too much about the exam. I hope that I can pass it, but if I don't, it's not a big deal.
Yeah, except we will tell all your students that you failed. So,
Yeah. I'm not worried about the math, but there is a lot of stuff here. I mean, it's not, the math isn't hard, but knowing when to use it is the hard part.
right. I always say that no part of this is difficult, but there's so much of it, that you
Yes.
just, there's a lot of information to digest. I think this 6-week format gives everybody a little more breathing room. But when I've presented this in a 1-week condensed class, people's brains are just fried by the time they
Oh,
take the
yeah.
exam. So, okie doke. So,
That's it.
yeah,
Okay. Thanks, Jay.
as soon as you finish the online course, it will allow you to generate your own certificate. You'll get a PDF certificate as soon as you've completed every module. So you'll have that immediately.
Okay, great.
Okay. All right. Well, I'll see you guys all 1 o'clock on Friday. Okay. Take care.
Thanks, Jay.
Uh-huh.